Okay, here we are, last lesson for Unit 5. This is Math 8, Unit 5, Lesson 22, called Volume as a Function of. And we're going to be comparing water heights in different containers. Today's lesson is really kind of putting some things together, maybe a little more complicated than others, so maybe one that your teacher does or doesn't do, but we'll do a little bit of video on it and I'll explain it as best I can. Some are a little more complicated, but we'll get there. All right, so first thing, a cylinder and sphere have the same height. I'm looking for missing information. So for example, we have a sphere, right? And it has a height, which is going to be the radius and the radius again. And we have a cylinder, which we don't know much about that yet, but it's also going to have the same height. If the sphere has a volume of 36 pi cubic units, what is the height of the cylinder? Okay, so to figure this out, what we can do is we can say that the volume of the sphere is 36 pi. Okay, if we set that equal to the formula for the volume of a sphere, 4/3 times pi times r to the third, we can figure out what the radius is going to be for that sphere. That radius times 2 is going to become the height of the cylinder potentially. All right, so to do that, we can multiply both sides by the reciprocal by 3/4. Okay, so 36 divided by 4 is 9. 9 times 3 is 27. So I'm left with 27. I can remove the pi's from both sides. 27 equals r to the third. So what number cubed gets you to 27? That's going to be 3. So we can tell that there's a radius of 3 for the sphere. Okay, with that in mind, knowing they have the same height, the height is going to be 2 of the radius. Okay, and since the radius is 3, 2 times 3 is going to be equal to 6. So that's the height of the cylinder. The cylinder is a height of 6. What is a possible volume for the cylinder? And be prepared to explain your reasoning. Now, since we don't actually know what the radius of the cylinder is going to be, we don't know. They didn't tell us it had the same volume, didn't say it had the same radius. We don't know what the radius is. We can't assume that it's going to be the same as what's over here. We can't assume it's 3. If it was 3, we could solve it. We don't actually know. There's information missing here from this problem. So the formula for the volume of a cylinder is volume equals pi times the radius squared times the height, which happens to be 6 in this case here. We don't have much more information besides that to be able to say what that's going to equal, unfortunately, right? So we're not really sure. We just know they have the same height, but that's all we know. We know the height of that, we know the volume of that, but we don't know if there's anything else in common with that radius to decide if we can make things kind of line up nicely together. If, for example, if the radius equaled 1, we would say that the volume would be 6 pi if it equaled 1. But we're not sure if that's what the radius is going to be. If the radius was equal to 3, like it was for the sphere, then you'd have 3 squared, which is 9, and then 9 times 6 is going to be 54 pi, right? So if it had the same radius as the sphere, it would have a greater volume, which makes sense, right? Because the cylinder is going to be a bigger volume than the sphere if they're sharing the same radius. But we don't know that. That's a big if. Let's look at the second part here, all right? Second part has a table here that wants you to fill out the table in the chart with basically some information. So we're going to fill in the missing volumes in terms of pi and add 2 more for what we got there. So this is volumes of a sphere. So the sphere is again 4/3 pi times r cubed. So for this one here with a radius of 2, that would be 4/3 times pi times 2 cubed. 2 cubed is 8. 8 times 4 is 32. So we end up with 32 over 3 pi. For this one here, I'm going to do it down below so I have space. We have 4/3 pi times 3 cubed. All right, so 3 cubed is like 3 squared if I eliminate this. So that's 9, and 9 times 4 is 36 pi. All right, this next one, it's 4/3 pi, and then we have 1/2 cubed. 1/2 cubed is 1/8, so this could be rewritten as 4/3 pi times 1/8. That can reduce to 2 and 1. And so we have 3 times 2 is 6 on the bottom and 1 on the top. So we could write this as 1/6 pi. For the 1/3, we can do 4/3 times pi, and then again 1/3 cubed. So that becomes 4 on the top still, and on the bottom we have 3 times 3 times 3 times 3, which is 81, and a pi there. All right. For the r value, this r is going to be simply the 4/3 pi times r cubed. So we just write the whole thing out, 4/3 pi r cubed. You could do some additional values there and fill that in. For the one that's 100, again, that's going to be a little larger. That's 4/3 times pi times 100 to the third power. 100 to the third power is going to be 1,000,000 times 4 is 4,000,000. So you end up with 4, 1, 2, 3, 1, 2, 3 over 3 pi. 4,000,000 and a third over and times pi. So how does the volume of a sphere with a radius 2 centimeter compare to the volume of a sphere radius 1? So the 2 is at 32 and a third pi. Compare that to 4/3 pi. So what's the difference here? Well, the difference is that this one is going to be 4 times 8. It's going to be 8 times larger, right? So when I go here to here and I double that, I'm going to do, when I double it, it becomes 2 to the third, which is 8 times more. Now looking at it when I have a radius of a half compared to one with a 1, that's comparing the 1/6 pi and comparing that to the 4/3 pi. So if I was doing comparison, that'd be like saying 1/6 divided by 4/3 as a comparison. That becomes 1/6 times 3 over 4, which becomes 3 over 24, or 1/8. And so in terms of going from cutting something in half, it becomes 1/8 the size. Right? So it's like dividing by 8. It's cutting into 8. This one becomes 8 times larger. This becomes 1/8 that way. So depending on what you're doing, okay? That can be written actually as, this one is written as whatever the size is, 2 to the third. This would actually be written as 2 to the negative third, but that's too much for us today. I'm thinking about a different class. Sorry. All right, moving over. A sphere has a radius of length r. All right. What happens to the volume of the sphere if its radius is doubled? So if we double the radius, then the volume is going to be, the double means times 2, is going to be cubed. So 2 cubed becomes 8 times larger. What happens to the volume of the sphere if the radius is halved? Okay, that's half cubed. That becomes 1/8 the size of the original. Okay. Sphere Q has a volume of 500 centimeters cubed. Sphere S is 1/5 as large. Okay, so the radius is 1/5 as large as that one. So what's the volume? Okay, so we're going to take the 1/5 and we're going to cube that. When we cube that, that comes out to 1 over 125. Now, it's going to be 101 and 125th the size of the original volume. The original volume was 500. So 500 divided by 125 is equal to 4. So in terms of a solution here, sphere S is going to have a volume of 4 centimeters cubed, which is 1/5 the volume of the original. All right. Okay, and the last one here, I'm going to do some parts of this here. It's a little unusual, but that's okay. Just thinking a little bit here. I think a lot of what's in here is, if you did a lot of the Are You Ready for More problems and things like that, this probably got you thinking about that. If you didn't, this is going to be maybe a little bit of a stretch for you. Okay, so first of all, we have 3 containers. We have a cylinder, we have a cone, and on the next page we have the sphere and a table that goes along with that one there. Okay, so they all, it says they're all filled with, the relation between volume of water is recorded in different ways. It's recorded as an equation, as a graph, and as a table or chart. So we're going to have to solve some problems here. It says the maximum volume of water the cylinder can hold is 24 pi. what is the radius of that cylinder? Okay, so the most water that a cylinder can hold is 24 pi. So we know that since it can hold 24, let me flip around a couple things here, sorry. For the cylinder, we had the height was equal to, it told us here that the height equals volume over 4 pi. Okay, so our volume, it says the max is 24 pi. So we can plug that in, and if we plug that in, what we end up looking at, well, let's move this around. I'm going to put this over here so that we have 4 pi times the height equals our volume, right? So since that's what we have set up here, oh, I had to write 4, should be volume. Volume should be V here. So looking at this setup here, this is rewriting our equation for the cylinder. Volume equals 4 pi h. The 4 represents the radius squared. So what number squared can get you to 4? That's going to be number 2. So the radius has to be 2 in order to get there. This extra information here, we probably could use it to solve something or else, but nothing quite yet. So we're going to leave it there for now. So we know the radius is going to be 2 for the cylinder. We don't have a cylinder. We could draw one here if we want to just draw a picture of one. You don't need to, but it has a cylinder, has a radius of 2. So it says graph the relationship between the volume of water poured into the cylinder and the height of water in the cylinder on the same axis as the cone. Okay, so to do that then we need to find out what the height is going to be. So if I use this value here, I can find out the height of the cone, which I would need to fill in with the graph here. So using that radius, we can say that the volume, the max volume we know is 24, right? 24 pi is the max volume, is equal to pi times the radius squared times the height, which we don't know. So this becomes 24 pi equals 4 pi times h. If I divide both sides by 4 pi, I can solve for what h is. So the height is going to be 24 divided by 4, which equals 6. So we know the height of the cone is going to be 6. That's one thing that we know. And so at 6, the volume of the cone is going to be 24 pi. Now look at our volume thing. It's in inches cubed. There's no 24 pi. So we need to do 24 and multiply that by 3.14. So that's 16, 4, and 5, and 12, put a 0 there, and 8, and a 2, and a 6. So we end up with 75.36 is what 24 pi actually is. And that happens at a height of 6. Okay, so we have a point here to plot. So at 75, it's a 60, 70, 75.6 at a height of 6. That is where our cylinder gets filled. Now it's going to fill at a constant rate, it said. So we're going to draw a straight line from here down to the origin there. Alright, and that's our cylinder. Just adding it on there. Here's our cone. You can see it fills up slowly and then starts to kind of taper off there. That's our cone. Okay, so the question was, what does this, okay, sorry, first it says graph the relationship, so we graph that there, no problem. What does the slope of this line represent? Well, our slope in this case is going to be the y over x, right? Slope is y over x, and our slope was at the height of 6, we're at 24 pi in terms of our height. So that means that essentially for every 1 inch we are going up 6 divided by 24 or filling up by 4 pi. That's how much water we're putting into the cylinder. So that's what the slope is telling us there. My answer keys does say something a little different there, but that's the numbers I'm working with, so I'm not quite sure why. That's okay. Which container can fit the largest volume of water and which one can fit the smallest? Okay. So we're going to compare some sizes here. So our water for the cylinder, first of all, since we know the cylinder we just figured out can hold 75.36, right? 75.36. the cone, we take a look at the cone's amount here, how much it can hold. The cone goes up and it seems to stop right about here, which has a point. We're not really sure what that's going to be exactly, but the cone stops somewhere about here, so that's going to be there. If this is counting 110, this is 130, so somewhere between 120 and 130, so maybe 125. Again, just estimating that there. And the sphere is interesting because the sphere's volume seems to, like, it goes up, and then as the height is increasing, it gets to 6. Then suddenly, like, the volume keeps increasing, but the height stays the same. I'm not sure what that is indicating there exactly, because if I have a sphere and I'm filling that up and I have a height in inches of 1, 2, 3, 4, 5, 6, at some point I'm out of space there, right? And so I'm gonna run out of room to fill this thing up at. So I'm not sure if that was supposed to be a 7 and an 8. I'm not really sure there what they're looking for. So what I'm thinking is that it only goes to 6, and that would be if it continued, but perhaps it can't continue. I'm not really positive on that one there. So I'm going to say the sphere is actually going to be 113 is where it stops. After that, more water is going in, but it's just not filling up. But again, I'm not positive there. So the largest one would be the cone, 125, and the smallest would be the cylinder at 75. Just a guess. Okay, about number 4. About how much water does it take for the cylinder and the sphere to have the same height? The cylinder and the sphere to have the same height. Well, one thing you might want to do, and this is just an idea, is if we combine all these things together, we can start to take a look at what might this mean. So what I mean by that is I have a line here for the cylinder and I have the cone. I can graph this one as well for the sphere. At a height of 1, we're at 8.38. So here's a height of 1, and we're going to be somewhere at about, well, that's 10, somewhere about here. We know it starts at 0, 0, so we're going to start there, 0, 0. At a height of 2, we're at 29, so about there. So 29 is about here at 2. At a height of 3, we're at 56, so 3, and we're going to come to 56, which is going to be about in the middle here. And 4 is at 83, so that's 90, 83, and so maybe about there. And 5, we're 104. 5, we're at 104, so here's the 100 line, so about there. And then 6, we're at 113. So again, that's 110, 113, and 6 is here at 113. And I'm not sure what that is, because it's still a 6 is at 120. And so it must like flatten out there, 120 and there. So this one's interesting because it's going to kind of curve here and then here and then there, and then it kind of stops like that. So that's what our with a pencil, our sphere is going to look like. So in terms of our question here about how much water does it take for the cylinder and the sphere to have the same height, like when do the cylinder and the sphere kind of cross each other? At what point are they the same height? And that's going to take place somewhere around here, right? So our same height is located there between, we'd say between 1 to 2 inches. Somewhere between there is where they have the same height. So I can show that graphically, it's a little easier to see there. Okay, when do the cylinder and cone have the same height? So the cylinder and cone seem to cross somewhere right about here. That's where they cross, and that's going to be, the height is going to be somewhere at about 4.5, right? Not quite sure exactly. When do they cross? So that's going to be between, yep, right, that's going to be here at about 4.5 inches. Or I could also look at in terms of the amount of water, which is going to be here at about a little more than 50. So, you know, someplace here-ish, so 55, 56, 55 inches cubed. You're talking about the amount of water there. Okay, just depends on which one you want to talk about. Okay, that works for that one. Let's get one last one, number 5, or 2 more actually. For what approximate range of volumes is the height of water in the cylinder greater than the height of water in the cone? So where is the height of the cylinder water greater than the cone? So here's our cylinder here, and this space right here is where the cylinder height is larger than the cone, all in that range right there. So where is that exactly taking place is the question for us. And so we would say that takes place between this point here, which we said is about 55 or so, again you can estimate, all the way to this point here, which is somewhere at about 100, almost 125, okay? So we could say 125, it's pretty close to 125. So in that space, from 55 to 125 inches squared, from 55 to 125, or sorry, inches cubed, is about where the cylinder is greater than the cone volume. Okay? And that's just what we see in that space right there. And for our last one, for what approximate range of volumes, again volumes, is the height of the water in the sphere less than the height of water in the cylinder? So sphere less than cylinder, talking about volumes. So where is the sphere volume less than the cylinder volume? That's going to be from this point here all the way to there. So where is this at? We said before this was somewhere at about like 15 or so, something like that, maybe 20, somewhere in that range, whatever. So maybe between 20 inches cubed, and then up to this point here where the curve touches, which is going to be 110, about 115 inches cubed, something approximately in that range. So this is going to be the space where we are less than the cylinder. So from this place to this place is that answer to number 6. Okay? All right, so a little strange, a little different, but kind of fun. That's it for this lesson and this unit. See you next time.